So these lessons on absolute values or moduli will consist of three parts. Firstly, theory, and here we will look at all the definitions and properties of absolute values. Then secondly, types of problems, all the types of problems that you need to be able to solve for moduli. And thirdly, a tutorial. Both parts 2 and 3 are based on an analysis of more than 20 past exams. This is the notation that we use for the modulus or the mod of A. We can also call it the absolute value of A. Let's take a few examples. The mod of 2 equals positive 2. The mod of negative 2 is also equal to positive 2. And the mod of 0 equals 0. From this we can see that the mod of any number A will always be greater than or equal to 0. Let's look at the basic application of this idea. Let's say we need to solve the equation, the mod of x equals 5. We know that both the mod of negative 5 and the mod of 5 will give us 5. So if you have the mod of x equals 5, from this we can see that x can be negative 5 or 5. So then our answer here will be x equals negative 5 or x equals 5. Let's take a second example. Let's say we need to solve the equation, the mod of 2x minus 3 equals 7. Since we know that both the mod of negative 7 and the mod of 7 will give us 7, we can see that what's inside the absolute values, in other words 2x minus 3, can equal negative 7, or 2x minus 3 can equal 7. And now we simply solve these two equations. So here we're going to have 2x equals negative 4, and of course x will equal negative 2. And here we're going to have 2x equals 10 and x is equal to 5. So our two answers then are x is negative 2 or x is 5. Let's look at the geometric meaning of the mod of A. The mod of a number A is a distance of A from 0 on the real axis. Let's take one or two examples. The mod of 3 equals 3, since the number 3 is 3 units away from 0 on the real axis. The mod of the number negative 3 is also equal to 3, since the number negative 3 is also 3 units away from 0 on the real axis. Then the mod of 0 equals 0, because the number 0 is 0 units away from itself on the real axis. Let's look at the geometric meaning of the mod of A minus B. The mod of A minus B is a distance between A and B on the real axis. To take an example, both the mod of 4 minus 1 and the mod of 1 minus 4 is equal to 3, since 1 and 4 are 3 units apart on the real axis. From this we can see that the mod of A minus B equals the mod of B minus A. Let's look at the geometric meaning of the mod of A plus B. We can rewrite the mod of A plus B as the mod of A minus negative B. Then, by our previous definition, the mod of A plus B is the distance between A and negative B on the real axis. To take an example, the mod of 2 plus 3 equals the mod of 2 minus negative 3. And since 2 and negative 3 are 5 units away from each other on the real axis, this equals 5. Let's look at the formal definition of the modulus function. The mod of x is defined as x if x is greater than or equal to 0, and it's defined as negative x if x is less than 0. This is what is known as a piecewise function. Let's take an example. Let's take the mod of 3. In this case, x is a positive number, so the mod of 3 will just be equal to 3 by this definition. Let's take the mod of negative 3. In this case, x is less than 0, a negative number, so the mod of negative 3 by this definition will equal minus negative 3, which is also equal to 3. Let's look at the graph of y equals the mod of x. We can draw a table and choose a few negative x values, 0, and a few positive x values. We can then find the corresponding y values, in other words the mod of our x values, and plot these on a system of axes. What we get is a V-shaped graph, and what's important to note is that when x is greater than or equal to 0, we have the line y equals x. And when x is less than 0, we have the line y equals negative x. You should note that the graph of y equals the mod of x is actually the graph of y equals x, where the part of the graph below the x-axis, in other words a negative part of the graph, is reflected in the x-axis. Just like any other function, the modulus function can also undergo transformations. Let's briefly look at some of these transformations. For simplicity's sake, let's assume that a is a positive constant. Then the graph of y equals the mod of x plus a is a graph of y equals the mod of x shifted up a units. The graph of y equals the mod of all of x plus a is a graph of y equals the mod of x shifted a units to the left. Then the graph of y equals the mod of ax, where a is greater than 1, is a graph of y equals the mod of x compressed horizontally by a scale factor of 1 over a. The graph of y equals the mod of ax, where a is between 0 and 1, is a graph of y equals the mod of x stretched horizontally by a factor of a. Let's look at the function y equals the mod of all of ax plus b. For simplicity's sake, let's assume that both a and b are positive constants. We want to write down the formal definition of this function. Firstly, we can find a critical value. Now, the critical value is the x-coordinate of the turning point of the graph. And we can get the critical value by making y equal to 0 and solving for x. So we get the mod of ax plus b equals 0, and then solving for x, we find that x equals negative b over a. Now we can write down the formal definition. The mod of ax plus b is equal to ax plus b if x is greater than or equal to negative b over a, and it's equal to the negative into ax plus b if x is less than the critical value. In other words, less than negative b over a. Of course, we can simplify the second part of this function by multiplying the negative into the brackets. So we can draw the graph of y equals the mod of ax plus b by drawing the line y equals ax plus b for x values greater than or equal to the critical value, and the line y equals negative ax minus b for x values less than the critical value. In this example, we have assumed that a and b are both positive constants. However, this doesn't have to be the case. Let's look at the geometric meaning of the mod of x less than a. The mod of x less than a implies both ways that x is between negative a and a. In other words, that x is greater than negative a, but less than a. Let's take an example. Let's say we want to solve the inequality, the mod of x less than 3. Then we are looking for all the numbers that are less than 3 units away from 0 on the real axis. And we can see that all the numbers between negative 3 and 3 will be less than 3 units away from 0. And hence, this inequality becomes x greater than negative 3, but less than 3. We can apply the previous rule to more complex inequalities involving the mod. Let's say we want to solve the inequality, the mod of x minus a less than b. Then, using the previous rule, we can see that x minus a will be greater than negative b, but less than b. Now we can isolate x by adding a through in the inequality, and the a's will cancel, so we end up with x greater than a minus b, but less than a plus b. In other words, the mod of x minus a less than b implies both ways that x is greater than a minus b, but less than a plus b. Let's look at an example. Let's say we want to solve the mod of x minus 2 less than 3. In this case, a is equal to 2 and b is equal to 3. So plugging into the above relation, we can see that x will be greater than 2 minus 3, but less than 2 plus 3. In other words, x will be greater than negative 1, but less than 5. Similarly, the mod of x less than or equal to a implies both ways that x is greater than or equal to negative a, but less than or equal to a. What about the geometric meaning of the mod of x greater than a? The mod of x greater than a implies both ways that x is less than negative a or x is greater than a. Let's take an example. Let's say we want to solve the inequality, the mod of x greater than 2. Then we are looking for all values on the real axis that are more than 2 units away from 0. And we can see that all numbers greater than 2 and less than negative 2 will be more than 2 units away from 0. And hence, the solution to this inequality will be x is less than negative 2 or x is greater than 2. Then similarly, the mod of x greater than or equal to a implies both ways that x is less than or equal to negative a, or x is greater than or equal to a. Let's look at squaring absolute values. Firstly, the mod of a squared equals a squared. In other words, when we take the mod of a number squared, it's equal to the number squared. In other words, the mod can fall away. We can drop the mod. Why is this? We know that any number squared is greater than or equal to 0. We also know that the mod of any number is greater than or equal to 0. So taking the mod of a number squared has no effect, and we can drop the mod. What happens when we square a mod? The mod of a plus or minus b all squared equals a plus or minus b all squared. In other words, when we square a mod, we can drop the mod. It has no effect. We can use this principle to solve equations and inequalities with that involve mods. Let's take an example. Let's say we need to solve the equation, the mod of x minus 2 equals 3. We can square both sides of the equation and the mod will fall away. So we end up with x minus 2 all squared equals 9. And then we can solve for x. And we find that x is negative 1 or 5.